Welcome back. We are in week 2 of covering waves. So everything we talked about last week is still important for this week. But one particular thing that I wanted to review before we move into new material is diffuse reflection. When we talked about diffuse reflection, all the light is shining onto the surface and then it's being reflected back, but it's being scattered when it does, so you don't get that mirror image. So today we're going to talk about diffuse reflection. So just wanted to make sure you remembered that term. Today we're going to cover just a couple of more details about light waves, and then we're going to talk about sound waves with some pretty fun stuff. So when we talked about light last week, we focused mostly on reflection of light, like when we talked about mirrors and that kind of stuff. But there's two other behaviors of light that we need to talk about. One is being absorbed by the object. And then the other one is being transmitted. And that means where light goes directly through the new material without any bending. If it bends, then that's refraction, the thing that we talked about last week. So transmission is going through the new material without any bending. How much light is transmitted is determined by what kind of material you're talking about. So if something is transparent, like a piece of glass, then it's transmitting all of the light. So none of the light's being reflected or absorbed, it's all being transmitted. On the other end, we have opaque, and those are things that aren't see-through at all because they're not transmitting any light. None of the light is making its way through the material. And then right there in the middle, you have translucent, where some of the light is being transmitted, some of it's getting through, but not all of it. So we can see through it, but not as clearly as transparent. So now we're going to go back to talk about reflection one more time. This time focusing on why we see things as certain colors. So before we get into that, just a quick review of the colors of the rainbow. So what we see as white light is actually 7 different colors of the rainbow. So red, orange, yellow, green, blue, indigo, and violet. And we're going to shorten it to a pretty common acronym for it, Roy G. Biv. So the colors of the rainbow in order from longest to shortest wavelengths. The reason why we're doing that is so we can talk about what kind of light is being absorbed and what kind of light is being reflected. So when white light hits a green leaf, it reflects the color green back to our eyes. And so we go, oh, hey, that leaf is green. Every other color of the rainbow, the Roy and the Biv, are being absorbed by the leaf. So we don't see those because the leaf is holding on to them. So the really key thing here is whatever color the thing looks to you is the color that it is reflecting to your eye. And this is true for black and white objects as well. So if you see something that looks white, it's because all of the colors of white light, the Roy, the G, and the Biv, are all being reflected back to your eyes. If you see something as black, it's actually the absence of reflection that you're seeing there because it's absorbing all of the white light and really not reflecting anything back to your eyes. Your eyes go, oh, hey, I don't see any light coming off of that thing, so it must be black. So that's why if you're outside on a really sunny day, you're going to feel warmer if you're wearing black clothes in comparison to if you're wearing white clothes, because the white clothes are going to reflect that light and heat from the sun, while a black shirt is going to hold on to that heat. All right, moving on to sound waves. So a couple of properties that are distinctive just for sound waves. The first one is intensity, and that's just how much energy is in that sound wave. So it affects how far away you can hear that sound. So quiet sounds have really low energy and really low intensity, while screaming at my computer has really high intensity. Ah! So, sorry, I just cracked myself up on that one. So how much intensity is in a sound is measured using the decibel scale. And you've probably heard of decibels before. So things that are just barely detectable by humans, we set at 0 decibels. Are there sounds quieter than that? Yes, but humans don't really care about those. Up to a normal conversation, maybe 50 or 60 decibels, and then all the way to extremely dangerous, extremely painful sounds above 120 decibels. These can actually just one and done cause permanent hearing loss. Like if a gun goes off near your ear and you don't have ear protection, it can actually cause hearing loss. But you're not out of the blue if you listen to stuff below 120. Because if you listen day in, day out to sounds over 85 decibels, that can impair your hearing. So that's why you see like certain jobs that require headphones or hearing protection, because even though the sound may not be super loud, if you're spending all day there, all week there, it does get to be kind of painful after a while. So another term that we need to review is frequency. We talked about that's how often the waves are passing in a certain amount of time. Well, we can't see waves, but we have the ability to hear different frequencies in sound waves. So pitch is the human perception of frequency. I'm sorry, I've got a typo there. It should say human perception of frequency. So it's how high or low pitch the sound is. So really high frequencies have really high pitch. Lower frequency waves have really lower pitch. And then the frequencies that we can hear are in just a certain little range there. So humans can hear 20 hertz, that's the unit of frequency, up to 20,000 hertz. And that's a pretty big range, but there's so many other sounds that are above or below that. So sounds that are below human perception, below 20 hertz, are called subsonic. Because if you think about like a submarine or a subway go down below, so subsonic goes down below what we can hear. Anything above 20,000 hertz is called ultrasonic. They're still sounds, we just can't hear them because they're above our range of what we can hear. How the frequency is squished together or spread apart is called the Doppler effect. If something is moving towards us, the waves get squished together, so we hear it as high-pitched. If they're moving away from us, those waves stretch out, and so we actually hear it as a lower pitch. And you have observed this, every single one of us have observed this with things like NASCAR. If the cars are coming towards you, they kind of do that sound as they pass by. Or if you hear like a siren coming towards you, it's like woo, 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 as it passes. You didn't know it's going to make all these ridiculous sounds today, did you? It's even more fun when we're in person with each other. Lots of ridiculous sounds. So here I'm just summarizing. As the objects move towards the observer, those waves are squished, and we know that the higher frequency the waves, we hear it as a higher pitched sound. Woo, 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 woo! And then as the object moves away, the sound waves are spread out, so we hear it as a lower frequency wave. Woo, 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 woo! Now this is true for all waves. Sound waves, obviously we can hear the difference, but you can pick this stuff up as well. So if you've ever heard of Doppler radar, which is what pretty much every news channel uses to talk about weather, they're using that same thing, they're just doing it with radio waves. So they measure the frequency of the radio waves, and if they're squished together, they know that the storm's moving towards us. If the waves are spread apart, then they know that the storm has passed by. So this is used in all kinds of different ways, not just in perceiving sounds.